We are a whisper of carbon in a universe of stone and gas. For centuries, our definition of life has been a mirror image of ourselves, creatures that breathe oxygen, drink liquid water, and build their bodies upon the four-bond elegance of the carbon atom. We call this the Goldilocks zone, not just a distance from a star, but a narrow chemical corridor. But this is a parochial view, a carbon narcissism. To a creature born in the liquid methane seas of a super-Earth or the supercritical fluid clouds of a gas giant, our temperate world would seem like a furnace, our chemistry, a chaotic explosion. If we are to truly find life among the stars, we must first learn to recognize its shadow biomes. We must move past the biology of the familiar and into the physics of the possible. Silicon, carbon's heavier cousin. It sits directly beneath carbon on the periodic table, sharing the same 4-Veloce electron configuration. But silicon has a breathing problem. When we metabolize carbon, we produce CO2, a gas easily expelled. When silicon reacts with oxygen, it produces SiO2, silica, quartz, sand. Imagine a creature that breathes oxygen and, as a result, fills its lungs with solid glass. On a planet like Earth, silicon-based life is a chemical impossibility. But raise the temperature, increase the pressure. In environments exceeding 500 degrees Celsius, the silicon-oxygen bond becomes more flexible. Here, we might find lithobiological entities, living crystals whose very respiration involves the cycling of molten silicates. Now, we move to the other extreme. Cold. Beyond the frost line, water is no longer a solvent. It is a mineral, as hard as granite. Here, on Titan, the seas are made of liquid methane and ethane. At minus 179 degrees Celsius, the very definition of metabolism changes. If life exists here, it uses a different architecture, the azotosome. These are theoretical membranes composed of nitrogen, carbon, and hydrogen. They require no oxygen. A Titanian organism might take 10,000 years to complete a single thought. To them, we would be nothing more than a blur of heat and radiation. If water is the solvent of the sun-drenched, and methane the solvent of the frozen, then ammonia is the Great Bridge. Ammonia remains liquid at temperatures ranging from minus 77 degrees Celsius to minus 33 degrees Celsius. It is a powerful solvent, capable of dissolving many organic compounds just as water does. On a high-pressure world, an ammonia-based biochemistry would be startlingly efficient. Their world would be a place of pale blue oceans and violet blood. What we learn from these shadow biomes is that life is not a chemical accident of carbon and water. It is a thermodynamic necessity. The hardware will change. It will be silicon in the fire, methane in the ice, and ammonia in the pressure. But the software, the drive to organize, to replicate, and to resist entropy, is a universal grammar. We are looking for ourselves in the stars, but we should be looking for the patterns. Life does not seek a specific element. It seeks a way to hold back the dark. The universe is not only stranger than we imagine, it is stranger than we can imagine.